Hello, my name is Fabio Cammelli, and in this video I'm going to show the work performed at the University of Delaware in Professor Vlacho's group. We developed a biphasic plasma microreactor that can directly convert ethane into liquid oxygenates, olefins, and hydrogen with only electricity and water. In this way, it is possible to upgrade an unutilized gas stream into valuable fuels and chemicals with easy separation between the liquid and the gas phase. Ethane is a relatively abundant resource, mostly present in natural and shale gas that can be transformed into value-added chemicals for polymer production, fuels, and solvents. However, ethane is not fully exploited, and it is extracted in remote areas where natural gas is often flared, since there is no economic advantage in transporting it and use it as a chemical feedstock. Therefore, decentralized gas-to-liquid transformation could create new opportunities for chemical manufacturing of valuable chemicals that are easy to transport while upgrading an underutilized resource. Our biphasic plasma microreactor offers an efficient route for decentralized gas-to-liquid transformation. The main working principle is reactive absorption, whereby the plasma discharge in the gas phase activates ethane molecules and water at the gas-liquid interface. Hence, we have alkyl and hydroxyl radicals that can recombine and form oxygenates that absorb in the liquid phase and remain separated from the gas phase, where ethylene is produced by ethane dehydrogenation together with hydrogen. There is also the byproduct of water dissociation. The reactor assembly is fairly simple and inherently modular. A tubular microtube is wrapped around a metal rod that functions as a ground electrode, whereas a copper foil covers the helical assembly. The geometry is linearly scalable by extending the tube and the electrode's length. The two-phase stream is produced by mixing in a T-junction a gas and a liquid stream that flow into the plastic tube as slug droplet flow. In this way, the liquid and the gas phase can be individually recovered at the reactor outlet. The reactive absorption scheme is based on electronic dissociation of a stable molecule like ethane in the plasma discharge, and at the same time it relies on the presence of water that functions as a source of the oxidizing agent, that is the hydroxyl radicals, and as a sink for the oxygenated bases that form at the gas-liquid interface from radical recombination. Therefore, by controlling the operating parameters that affect the plasma discharge and the gas-liquid interface, it is possible to tune the product selectivity. The first parameter we studied is dissipated power. By increasing the applied voltage between the two electrodes, it is possible to increase the ethane conversion and in turn the production of oxygenates. In fact, increasing power leads to high electron density and dissociation of both ethane and water. However, ethylene is also subject to electronic dissociation, thus its selectivity drops at higher power. Hydrogen is the byproduct of electronic dissociation of ethane and water, therefore its productivity is the highest at the maximum applied power. Another way to tune product selectivity is to feed different fractions of ethane in the argon stream used as the carrier gas for the plasma. By keeping the applied voltage constant, high ethane concentrations result in lower conversion, as plasma is more difficultly ignited due to the high breakdown voltage of ethane. As a result of lower power channeling to discharge, ethylene is the main product, whereas oxygenates are preferentially generated with a more diluted stream of ethane. Hydrogen production derives exclusively from electronic dissociation. Hence, low ethane fractions are preferable as more ethane and water are activated by the plasma. The last parameter that we investigated is liquid flow rate at constant gas flow rate. In this way, we can control the interfacial area where absorption takes place, and we can also optimize production rate. At low liquid flow rates, more interfacial area is generated in the slug flow, hence more water evaporates and dissociates, and more oxygenates absorb in the liquid phase. Nonetheless, the productivity of the liquid oxygenates is directly dependent on liquid flow rate. Therefore, a trade-off exists between 0.2 and 0.3 milliliter per minute. Finally, I want to thank the funding agencies that supported this work, my collaborators, and you for your interest in this video and for sticking to the end.